In this video, we'll talk about how to use Wireshark to analyze packet captures. We'll assume that you've downloaded Wireshark and you've installed that, and I'll assume that you know how to open a packet capture file within Wireshark, and you should know how to do this based upon your previous experience with opening files in Windows. And this also assumes that you've got a packet capture. You should have watched the TCP/IP videos as well as how to capture packets with WinDump, and so you should already have a PCAP file. That is a packet capture file with the extension .pcap. Is a packet capture file. So essentially what we did was we used this program called TCP dump to actually capture some packets that were running over a network, and this is one of the packet captures that were this is a file called Ethereal, and what it does is you can actually use it to capture packets as well as to analyze them. And essentially what it does is it takes the binary file and actually parses it into sequences that are interpretable by a human being. For example, over here we see that here's packet number 1, 2, 3, 4, 5, and so on down the line. You can scroll down to see those. Notice this is the time, it's offset, it's relative, so this is when the first packet came in. Of course that would be at 0, and the next one is at 51 here, 104, and all the way once you get up to here it would be seconds if you have anything in this column. Here's the source address, the source IP. This is a destination address, and if you take a look at those, and based upon one of the other lectures, you know that is what type of address? Anyone? That's it's a private IP address. So that's an address that was doled out by a router using network address translation. So these are not routable over the internet, only behind the router. Notice over here we have the protocol that is being used, and then over here notice that this will actually be the source. Notice that the arrow is going this way. So we have a source and a destination. So this is sending, this is receiving. Over here this is the port number that's sending. This is a port number that's receiving. This is a send packet. So what is this trying to do? This is trying to initiate a three-way handshake between this computer and this computer. Here's the sequence number. These are relative as well. And the length in a send packet, the length will always be 0. And if you look at this, and if you don't already know, notice that this destination is sending a packet, a send packet, from this port to this port on this computer to this port on the same computer. So essentially what's happening is that this is it's doing a scan. It's trying to determine which ports are open by sending a send packet, because typically what will happen if this computer sends a send packet to this computer over this port, if this port is actually running anything, a service on port 1, that this will respond with a SYNAC, a send and an ACK. Okay? So now if we look down here, we can see that this packet has now been parsed into its individual elements here. Remember that we talked about packets are encapsulated, and so here we see the encapsulation starts, this is the innermost packet all the way up to the outermost packet here. And so this is the frame packet. Tells you 60 bytes that were captured, the frame number, the packet length, the capture length, and so on. The protocols in the frame, isn't this great? It has Ethernet, IP, and TCP, so it's actually broken. Ethereal has broken this down and indicated what is actually encapsulated within this packet. It tells about a coloring scheme and or a coloring rule. Now this is not part of the actual packet. This is just ethereal reporting on it. If we go down to the Ethernet layer right here, we see that we have some addresses here in hex, and these is going to be the MAC address, media access control, which is the hardware address of the Ethernet network interface card. And so the source packet is this, the destination packet is this. And we see even more information down here. Notice that it's a unicast frame. It tells you even more about the MAC address right here, but what we're really interested in is down here. Let's look at the Internet Protocol layer, and this just gives us the information regarding the source and the destination, which of course we have up here as well. With a version number of IP, it's IP version 4. There's also an IP version 6. We'll talk about that later on. The header length is going to be 20 bytes. The services field is not important right now. We'll talk a little bit about that later. Let's see what else is encapsulated in here. The flags, there's a reserve bit, a don't fragment bit. Notice that none of these are set. It doesn't need fragmentation because it doesn't really have any data. Time to live is 49, which I've discussed before, and the protocol that's encapsulated is hex and 6, and hex and 6 will be TCP. The header checksum, notice that that's correct, and the header checksum indicates whether this packet was received intact, because if it doesn't, remember that TCP is a reliable protocol, and so if it is received and for some reason the checksums don't match once the packet is received, then the destination will actually send back a message to the store saying, please resend this packet. And finally, at the TCP level, we're going to have the ports. Notice that it's the same information that we've got up here: the sending port and the receiving port, the relative sequence number and the length. And of course, it has that listed in here. The header length is going to be 20 bytes. It's got the flag that is set here. These are all the different flags that are available. The ones that we're concerned with here are the send flag. And notice that the window size, this is the amount of available space in the TCP window. And once again, the checksum. If we move down here, and of course that's the last information that's set, because we're not really sending any data. All we're really sending right here is, in other words, there's no application information involved with this. There's just a connection that's attempting to be made between this computer and this computer. And so down here, all the information contained in here is actually contained right in here. All the information. So if we go up here, notice we click on the send right here. Notice that it's actually indicated where that's set right in here. Window size right here. This is in hex. And the checksum. 24A5, and there it is in hex. Because this is in hex, notice that this will match. Okay, let's take a quick look at another protocol. Here's ARP for Address Resolution Protocol. And if you recall from your previous studies, that when a packet comes into the gateway router, it doesn't know which computer the router may not know which computer has which address, IP address, because with DHCP those things can change. However, what doesn't change is the computer's MAC address, or at least it shouldn't be changing. Those should be static. So when the packet comes in, if the router or gateway computer doesn't have the mapping between the IP address and the MAC address, and it's what it's called its ARP table, what it does is that it sends a broadcast address out to everything on the network, requesting the mapping between here an IP address and a MAC address. And so see right here, this computer, the source is the Dell right here, sending out a broadcast address to everybody in ARP, who has 192.168.54.1. Tell this IP address right here, and this IP address is actually this computer right here. And we see here that this is actually a MAC address, and this returns the packet that has the answer to this address, and it says 192.168.54.1 is at this MAC address. And after that, then that packet and all other packets are sent. When that comes in, a packet with this destination address, it goes to this MAC address. So remember that that on a computer network, that the computers are uniquely identified by their MAC address, not by their IP address. And geez, I hope that was cogent. I believe it was. I hope that was clear. Okay, let's look at some other things. We see lots of TCP involved here. Most of these are attacks right here. Or actually, this is scanning. And then there's a reset act that's being sent by this computer because this port is not being used. And okay, what we're going to do is you keep looking down here. They're all TCP. What we want to do is just look at an application level, something I went over before in DNS. So what we're going to do is we're actually going to run some live demonstrations in here shortly. Okay, well here's HTTP right here. So now we're talking about an application level. Let's look at this, then we'll run some DNS examples. Okay, so we have the frame level, we have the Ethernet level right here. We've already looked at the IP address. Here we see, if we're looking at this right here, that the source address is this, the destination is this. And we already looked at the header length and the version and so on. Let's get down to TCP level. And notice that this source port is being used and this destination port is 80, and we know 80 is HTTP. Right here. And notice that the flags set are push and an acknowledgement. And so when we click on this, we see that's what we have right here, push and acknowledgement. That really doesn't tell you anything because it's in hexadecimal format, but that's the good thing about Ethereal. It kind of breaks everything down for you. It parses everything. Now notice what we didn't see before is we actually have an application layer level on here, which is HTTP, okay? And so this is the actual command that was sent. Notice that part of it is listed right here. The requested method is get a particular site, a particular web page, and notice that all this right here is what is being requested right here. Whoops. Along with some options. So that's what's being requested. The requested version is HTTP 1.1 and the host name, and it will accept these types of images, the accepting language and the accepted character set. All of this is being sent, notice, with this right here. So this will be the innermost data of the packet that is being sent. And so this is encapsulated in this is encapsulated in this is encapsulated in this, and finally this is encapsulated in that. And so that's why it's shown this way on here. Okay, one thing interesting about Ethereal is if you actually want to follow this stream, notice that these are not in order, right? Because here you have an HTTP GET, and then here you have, actually this might be in order. Let me take a look at this for a second. Yes, that's actually in order, but if you want to look at the entire stream, the entire conversation between these two, you can double click on hopefully the first one in here, which actually that's not the first one because the first one would be a SYN. Here we go. Oh, notice that these three right here, the SYN, a SYNAC, and an ACK, that's our three-way handshake right here. So .19 is trying to make a connection to .45. So we have our three-way handshake here. And so then we can say follow TCP stream. There we go. And actually what this does is this shows us the entire conversation between the two computers. So at first this GET was being called for by this computer right here. This is the initiating computer, the source. And the destination address simply said this is not found, and this is what it returned. foo.jsp was not found on this server. So that's the entire conversation that took place between this computer and that computer. There we go. So we can close that. Now let's look at one more. It's going to take me a second to set this up, so I'll need to pause this for a second, and we'll look at how DNS works. Okay, let me show you how to run Ethereal. Realize you could run this on your own computer, and if you're connected to a switch, because you'd only be listening in on your own conversations. If you're connected to a hub, or you're trying to do this from a network port span port rather, you're going to be breaking the law. You can be breaking Title 13 of the Wiretap Act, and that's against the law. So you can run this on your own just to listen to the packets that you're sending and receiving from your own computer, but you shouldn't do this to listen to anybody else. It is against the law. So the first thing we want to do is that we want to set up a capture. And the first thing we're going to do is go to options, and what we need to do is we need to, since there may be more than one network interface card listening on here, the ability to listen, we need to select one. See, we have a dial-up adapter, and then I've got VMware installed as well. We don't want to listen on those, so we select our gigabit Ethernet driver from Broadcom. Okay, a lot of this stuff you don't need to change in here. You can, though, if you like. We want to capture packets in promiscuous mode. It says if you want to capture all the traffic that the network card can see, mark this option. Oh, because I'm sitting back on a network address translation behind that, then it's going to capture everything on my network, but it's all mine anyway. So for for right now, if you're sitting on your own network, you shouldn't be using this. So you want to click off Capture Packets in Promiscuous Mode. You want to update list of packets in real time so you can just see them flowing across. Automatic scrolling and live capture, you can do that if you want. And then these are the standard defaults. Enable MAC name resolution, enable transport name resolution. And so we can click Start, and then what we see is the packets are going to fly by. Okay, so in here this is indicating what types of packets. It's giving a running overview of everything. And then in here we see, notice there's some DHCP and ARP going on right here. Cups is for printing. And now what we want to do is we want to open a browser. And I want to move this. There we go. Okay. And then what's happening in the background is, there we go. So my browser's open, so now I know that I've got some DNS packets. So I'm going to stop right there. Now we can go back up to the top and see what's going on. So Internet Printing Protocol. This is my computer, my Mac, that's broadcasting to everybody saying that I'm available for printing. DHCP is being run right here. Samba is used for sharing information between Windows computers and other types of computers or other Windows computers. Notice this is Windows networks are very chatty, you'll see. If I did the same thing over on my Mac, I wouldn't get nearly as many packets if it wasn't connected, if I didn't have any Windows boxes connected to the network. Okay, what we're going to do is we're going to go down here and look for DNS. Here we go. Okay, here's our first one. So, and in fact, this has got a great capability, Ethereal does, of creating expressions for actually filtering out different types of packets. There's thousands upon thousands of different types of queries that you can set up. So instead of looking at a ton of information, you can pare it down to just a few packets. And one of those, just to show the DNS, is filtered the DNS.ID. So I only want to look at DNS packets. I click Apply, and there's two of them. It makes it really easy. So let's look at the first one. Notice this says a standard query, www.google.com. Okay, let's go down to Internet Protocol right here. Notice that this box is 192.168.0.7, and the destination port for DNS, as I've had it set up, is the gateway address, okay, which is my router, which actually doesn't contain the DNS information. It has to send it out to another DNS name server or name server, which is set up. Source port is this. Notice that any of the source ports typically for a client initiating a request are going to be greater than 1023, and because those are the usually the client ports. Anything under 1024 are going to be well-known ports or registered ports, and those usually require root to run those. And so that's why we know that this is a client requesting, or we presume it's a client, because it's actually above 1023. Notice that the destination port is domain, and domain is usually 53. That's the standard that's been set. Notice over here that this is not a TCP, it's a UDP. And recall the difference between UDP and TCP is the fact that this is connectionless, and therefore it's unreliable. However, this is considered good enough because usually you get a response back. If you don't, in a specific set of time, this request times out, and then another request will be sent out. So notice that we didn't receive any error in here. So the source port, destination port, the length, and the checksum, that's all the information that was in this UDP. And then at the application level, the domain name system was the actual query. And so this lists all the information about the DNS. And what we really want to do is look at the actual query down here. And what the query is saying is, hey, what is the IP address of www.google.com? And if we go up here to the next packet, We received it very quickly. Let's go back up. Notice that once again the response is from a UDP packet. The domain name system down here. Here we have the queries again, but we also have the answers and the authoritative answers. So this indicates that www.google.com has the following IPs: 64.233.179.104 and .99 down here. And so now the actual communications between this computer and Google can occur. The authoritative name servers for Google are these computers, and that means that they are the ones that hold the authoritative name, that these will always give you the correct IP addresses. If an IP address for Google.com ever changes, they will first be changed in any of these name servers, and then that information has to be updated in other name servers. And that's why you should always get a correct answer for an IP address to domain name mapping if you use an authoritative name server. So what that did was it gave you a little clear overview of TCP, IP, and the different levels of encapsulation that occur. You learned about IP, Ethernet, ARP, DNS, a little bit of HTTP, and this gives you a good visual indication of encapsulation.